You think temperature is what you feel. Touch metal, cold, touch wood, warm, same room, same air, same temperature for hours, but one feels cold and one feels warm. You've felt this your entire life. Every single person on earth has experienced this. But you never really asked why. You just accepted it. Metal is cold, wood is warm, but that's not an answer. That's just repeating what you feel. When you really ask why, you discover something so strange, it changes everything you think you know about heat, about temperature, about what cold even means. Feynman spent years teaching this exact problem, and once you understand it, you'll never touch anything the same way again. Let's start with something simple, something everyone knows. You walk into a room, you've been outside, hot day, you step inside. Air conditioning, cool air, you stand there, you feel cooler, fine, that makes sense. The air is cooler than your skin. Heat moves from hot to cold. You learned this in school. Your body is 98.6 degrees Fahrenheit. The room is 72 degrees. Heat flows from your skin to the air. You cool down. Everyone understands this. But here's the thing. Now touch a metal doorknob in that same room. It feels cold, really cold, not cool, cold. Then touch the wooden door frame. It feels warm, barely cool, maybe even neutral. But wait, they're both in the same room. They've both been sitting there for hours. Same air, same temperature. The metal and the wood are both 72 degrees, exactly the same. So why does the metal feel like ice and the wood feel like nothing? Think about it. Really think about it. If temperature is what you feel and both objects are the same temperature, you should feel the same thing when you touch them. But you don't. The metal feels dramatically colder. Not slightly. Dramatically. You can feel the difference instantly. In a fraction of a second. Your brain registers metal equals cold, wood equals not cold. But the thermometer says they're identical. So what's happening? Are your nerves lying? Is the metal actually colder? Did it somehow stay cold when everything else warmed up? None of those make sense. The metal has been sitting there just as long as the wood. It's in thermal equilibrium with the room. It has to be the same temperature. Here's where most people stop thinking. They just accept the mystery. Metal feels cold. That's just how it is. But Feynman never stopped there. He'd grab you by the shoulder and say, listen, when something doesn't make sense, it's because you're asking the wrong question. You're asking why the metal is colder, but it's not colder. They're the same temperature. So the question isn't about the metal's temperature. The question is about what you're actually feeling when you touch something. And here's the answer that's going to frustrate you. You don't feel temperature. You've never felt temperature. Not once in your entire life. What you feel is heat leaving your body. Let me say that again. When you touch something that feels cold, you're not measuring its temperature. You're measuring how fast it's stealing heat from your skin. This is important. Your skin is 91 degrees Fahrenheit on the surface. That's warmer than the room. When you touch anything at room temperature, heat flows from your skin into that object, always, from hot to cold. That's the second law of thermodynamics. Heat must flow. It has no choice. But here's what changes everything. Different materials steal heat at different speeds. Metal steals heat fast, insanely fast. Wood steals heat slowly, really slowly. The metal pulls heat out of your skin so quickly that your skin temperature drops. Your nerves detect that temperature drop. Your brain interprets it as cold. The wood pulls heat so slowly that your skin temperature barely changes. Your nerves detect almost nothing. Your brain interprets it as neutral, maybe even warm. Both objects are 72 degrees, but one rips heat away. The other barely touches it. Now watch what happens when you understand this. Let me take you to your hand. Zoom in. Your skin. Molecules. Vibrating. That's what temperature is. Molecular vibration. Kinetic energy. The hotter something is, the faster its molecules move. Your skin molecules are vibrating fast. 91 degrees worth of fast. You touch metal. The metal molecules are vibrating slower. 72 degrees worth. At the point of contact, your fast-moving skin molecules slam into slower-moving metal molecules. Energy transfers. Your molecules slow down, metal molecules speed up. This happens instantly, but the metal doesn't just take that energy and hold it at the surface. It conducts it away, deep into the metal, fast, really fast. Thermal conductivity, that's the term. How quickly a material moves heat through itself. And here are the numbers that reveal everything. Thermal conductivity is measured in watts per meter Kelvin. Sounds complicated, it's not. It's just how much heat flows through 1 meter of material for every degree of temperature difference. Aluminum, common metal, about 205 watts per meter Kelvin. Steel, about 50. Copper, 385. Now wood, pine wood, about 0.12 watts per meter Kelvin. Let me say that again. Aluminum conducts heat 1/700 times faster than pine wood. 1/700 times, not twice as fast, not 10 times, 1/1700 times. When you touch aluminum, it yanks heat out of your skin and spreads it through the metal so fast that the surface never warms up. Your skin keeps losing heat. The temperature keeps dropping. You feel cold. When you touch wood, it takes heat so slowly that it can't conduct it away fast enough. The surface warms up almost immediately. Heat stops flowing. Your skin temperature stays stable. You feel nothing. Or you feel slightly warm. Think about it like this. Imagine you're trying to cool down a hot cup of coffee. You pour it into a metal cup. The metal heats up instantly. You can't even hold it. The coffee's heat spreads through the entire metal cup in seconds. Now pour the same coffee into a wooden cup. The wood barely gets warm. Why? The wood is a terrible conductor. The heat stays trapped near the surface. It can't spread. Same principle with your hand. The metal cup pulled heat from the coffee and spread it everywhere. The wooden cup couldn't. Your skin is the coffee. The metal doorknob is the metal cup. It steals your heat and conducts it away before you can warm up the surface. The wooden door frame can't conduct the heat away. The surface warms up. Heat transfer slows. You feel warm or neutral, but wait, let me show you something even stranger. Go outside on a winter day, 0 degrees Fahrenheit, brutal cold. Touch a metal pole, you know what happens. It feels like it's burning, instant searing cold. Your skin can freeze to it in seconds. Now touch a wooden fence post, same temperature, 0 degrees, but it just feels cold. Uncomfortable, sure, but nothing like the metal. Why? Same reason amplified. The temperature difference between your skin and the metal is huge now. 91 degrees skin, 0 degrees metal. 91 degree difference. Heat flows fast, really fast. The metal's high thermal conductivity rips heat out of your skin so quickly that your skin temperature plummets. Water in your skin cells can actually freeze. Frostbite. The wood has the same temperature, but its terrible thermal conductivity means heat leaves your skin slowly. Your blood flow can almost keep up. Your skin stays above freezing. No damage. Let's test this understanding. Feynman loved this part. Prediction. If this theory is right, if it's really about thermal conductivity and not temperature, then we should be able to predict what other materials feel like. Carpet, thermal conductivity about 0.06, lower than wood. Carpet should feel warmer than wood. Touch carpet and wood in the same room. It does. Carpet feels warmest. Tile floor. Thermal conductivity about 1.0. Higher than wood, lower than metal. Tile should feel colder than wood, warmer than metal. Touch them. It does. Exactly as predicted. Marble. Thermal conductivity about 2.5. Colder than tile, warmer than metal. Touch it. Perfect match. The theory works. Every single material lines up exactly where thermal conductivity predicts it should. This isn't speculation. This is measured. This is real. And here's where it gets beautiful. Scientists can measure thermal conductivity precisely, not just rough estimates, precise measurements. They use steady-state methods. Hot plate on one side of material, cold plate on other side. Measure temperature difference, measure heat flow, calculate conductivity, or they use transient methods, flash of heat. Watch how fast it spreads. Different methods, same results. We know exactly how fast every material conducts heat. Diamond, the champion, 2200 watts per meter Kelvin. Styrofoam, the insulator, 0.03. Your skin sits there at about 0.3, right in the middle. So anything above 0.3 feels cold because it pulls heat faster than your skin can conduct it away internally. Anything below 0.3 feels warm because your skin conducts heat to the surface faster than the material can take it away. The surface warms up. You feel warm, but let me take you deeper. Why do materials have different thermal conductivity? What makes metal so good at conducting heat and wood so terrible? It comes down to structure, atomic structure. Metal is a lattice of atoms with free electrons, millions of free electrons flowing through the structure. These electrons carry heat. When you heat one part of metal, those electrons zoom to the cooler part. They're fast. They're efficient. They transfer energy through the entire structure almost instantly. That's why metal conducts electricity too. Same free electrons. Wood is different. Wood is organic. Long chain molecules, cellulose, lignin, bound electrons. No free electrons flowing around. Heat has to transfer atom to atom through vibrations. Slow, really slow. Each molecule vibrates, bumps into its neighbor, transfers some energy, and that neighbor bumps into its neighbor. It's like passing a message person to person versus sending an email. The metal emails the heat instantly. The wood passes it person to person, slow and inefficient. Now here's the thing that broke Feynman's students' brains. Air. What about air? You're surrounded by air all the time. Air at room temperature, 72 degrees. Why doesn't air feel cold? Your skin is 91 degrees. Heat should flow into the air. You should feel cold constantly, but you don't. You feel neutral, comfortable. Why? Thermal conductivity. Air is an incredible insulator. Thermal conductivity about 0.026. Lower than styrofoam. Lower than almost anything. Air conducts heat so slowly that even though heat is flowing from your skin into the air, it flows so slowly that your body heat production keeps up. Your metabolism generates heat. Your blood delivers it to your skin. The rate of heat production equals the rate of heat loss to still air. Your skin temperature stays constant. You feel neutral, but move the air, create wind. Now the air that you warmed up gets replaced with cold air continuously. You can't warm up the boundary layer. Heat loss increases. You feel cold. Wind, chill, same air temperature. Faster heat loss, feels colder. Let me show you one more layer. Your perception of temperature is logarithmic, not linear. This is subtle but important. When the metal pulls heat from your skin twice as fast, it doesn't feel twice as cold. It feels maybe 20% colder. Your nerves respond to the rate of change. not the absolute rate. That's why you stop noticing temperature after a few seconds. You touch something cold. It feels cold. Wait 10 seconds. Still touching it. Feels less cold. Not because it got warmer, because your nerves adapted. The rate of change decreased. Your skin reached a new equilibrium temperature, lower than before, but stable. No more change. Your nerves quiet down. You stop feeling it. This is why cold water feels freezing when you first step in, but fine after a minute. The water didn't change temperature. Your skin did. Your nerves adapted. Same water, different feeling. So let's bring this all together. Why does metal feel colder than wood when they're the same temperature? Because you don't feel temperature. You feel heat transfer. Heat flows from your warm skin to the cooler object. Always, but the rate of heat flow depends on thermal conductivity. Metal has high thermal conductivity. It conducts heat away from the contact surface fast. Your skin keeps losing heat, temperature drops, nerves fire, you feel cold. Wood has low thermal conductivity. It conducts heat slowly. The surface warms up. Heat transfer slows. Your skin temperature stays stable. You feel neutral or warm. Both objects are the same temperature, but they interact with your body differently. Temperature is a property of the object. What you feel is a property of the interaction. The metal isn't colder, it just steals heat faster. The wood isn't warmer, it just steals heat slower. Your body is the only thing changing temperature, and that's what you feel. And here's what this reveals about reality. The world doesn't match your perception. You walk through life feeling hot and cold, assuming you're measuring temperature, but you're not. You're measuring thermal conductivity weighted by temperature difference. Your senses evolved to protect you from harm, not to measure physics accurately. Touching very hot metal kills you, burns, tissue damage. Touching very cold metal kills you, frostbite, cell death. Your nerves scream warnings when heat transfer is dangerous, but those warnings feel like temperature. Your brain built a model. Cold things are dangerous, hot things are dangerous, warm things are safe. Useful model, keeps you alive. But it's wrong. The danger isn't the temperature, it's the heat transfer rate. A 200-degree oven, dangerous. But you can stick your hand in for a second and be fine. Why? Air. Terrible conductor. Heat transfers slowly. Your skin doesn't burn instantly. But a 200-degree metal pan, touch it for 1/10 of a second. Instant burn, blisters, skin damage, same temperature, different conductivity, different harm. This is what Feynman meant when he said the world is not what it seems. You think you experience reality directly. You don't. You experience your nervous system's interpretation of reality. And that interpretation is shaped by evolution, by survival, not by physics. Your eyes don't show you photons. They show you colors and shapes that helped your ancestors find food and avoid predators. Your ears don't show you pressure waves. They show you sounds that signal danger or communication. Your skin doesn't show you temperature. It shows you heat transfer rates that predict tissue damage. Reality is photons and waves and molecular vibration. Perception is the user interface your brain built to navigate that reality without understanding it. And usually it works fine. You don't need to know thermal conductivity to avoid burns. You just need to feel cold equals danger. But sometimes you want truth, not comfort, not simplicity. truth, and truth requires looking past what you feel, asking why you feel it, and discovering that the answer shatters the simple story your brain tells you. The metal isn't cold, you're measuring conductivity. The wood isn't warm, you're measuring poor conductivity. Temperature is the same, feeling is different. And once you see this, you can't unsee it. Every time you touch something for the rest of your life, you'll know. You're not feeling the object's temperature. You're feeling heat racing out of your skin. Thermal conductivity made tangible. Physics happening in real time. Your body as an experimental apparatus, constantly measuring heat transfer, reporting results as sensations, hot, cold, warm, cool. Every sensation is data. Every touch is an experiment. The universe revealing itself through your fingertips, not the universe as you thought it was, the universe as it actually is, strange, precise, beautiful, and completely indifferent to what you expected to feel.